if the data is all that is known, you must agree with me that it's not rational to add things to your model that aren't indicated by the data. Fair enough? Okay, so given that, is it better to be over-constrained or under-constrained in machine learning? Over-constrained, clearly. If you're under-constrained, all bets are off, your model sucks. If you're over-constrained, your model might be good. And now we get to this problem. Which model's best, red, green, or blue? That's getting a little messy. Let's get rid of some of the new craft. There. Red, green, or blue, which model's best? So Occam's razor, according to Occam's razor, which model is best? Let's do it that way, because we've got to agree on the assumptions. According to Occam's razor,
blue is the least error over there on the right. That's where we go.
According to Occam's razor, green is an okay model, and anything more complex than green you should reject. Occam's razor has nothing to say about getting more simple than the data says to get. Occam's razor only says don't be more complex than is justified by the data. Can I say that this green complexity is justified by the data? I can, because this error is lower than this error, and therefore there is some justification for going from blue to green. That justification is 1.38247 amount of error. Suppose there were two models that both had SSE equals 0. Let's do a purple model. So it's not as wiggly as green, but it still perfectly hits all the data points. Now Occam's razor says, don't do green, do one of the other models. Because Occam's razor says, don't do anything more complex than is necessary to perfectly fit all your training data. I'm going to claim that Occam's razor, however, is not enough, because in general, you can tell green's a pretty sucky model, can't you? I mean, it is. Blue is better. Which is better, red or blue? I don't know. I don't even know that blue's better than green. Green might be better than blue. But given my experience, blue's going to do a pretty decent job. Red will probably be good too. Green's going to be really bad. How do we determine that functionally or in a algorithmic manner? Anybody done anything like this before? All right, I'll tell you what I'm fishing for. I am fishing for somebody to say the word cross-validation. Yeah, here's what cross-validation is. Basically, imagine we took half of our data points. Well, imagine even though the now is right here and this is all the data we've really got, suppose we pretend now is right then. And then we train our model on these data points that are in the past of the past. And we compare, now the models aren't even going to be this good, right? They're going to be a little worse because we're fitting to less data. But then they're going to make predictions, and at least in this range between the fake past and the present, we have some data we can test, and we can see which model does the best, right? And if we test which model does the best on this holdout data, so we were trained on this, we're testing on that, then we get a number that we get to slap on that's not error against the training data. In machine learning, measuring error against the training data is generally considered cheating. It's basically, you showed me this data, and then you quizzed me on exactly the same data. That would be as worthless and pointless as school, right? It was supposed to be funny. Nobody laughed. Whereas, if you train on this data and then test on that data, now we're moving from elementary school to college, right? Where all of a sudden the test doesn't look exactly like the homework assignment. Now you're having to actually learn something. So when you do machine learning, it's very important not to allow a single point that was ever in your training data to also bleed into your test data, because as soon as you do, all bets are off. If it were a cheating machine learning algorithm, it would remember, and then it would regurgitate and get a better score than is reasonable, and then you wouldn't know. Okay? Cross-validation makes sure that doesn't happen because we throw out our model between every fold, and each fold only trains on some portion of the data and tests on some different portion of the data. Do you see why we did what we did? Cross-validation is, I'm going to claim, in many ways greater than Occam's razor. Because whereas Occam's razor says, make your model simpler and simpler and simpler until you can't justify it with your training data anymore, cross-validation says, and keep on going until you can't get any better accuracy. So cross-validation usually says, go even simpler than Occam's razor says. It means go until your model makes the best possible predictions on the parts you're not using to train with. And that will answer the question, which is better, blue, green, or red? Basically, we do cross-validation, whichever gives the best score. As far as we can tell, that's the best model for the future. Of course, we won't know until we see the future, but at least in the present, if we want to know the future, cross-validation is the best thing we've got. It's the nearest that there is to being able to slap a number on how good your model is. And presumably, if we do cross-validation, then we gather more data and then do it again, the number shouldn't change very much. If it does, you didn't have very much data in the first place, or your model wasn't sufficiently trained, or something like that. Okay? Did anybody write a unit test with OLS and under-constrain your model and find that your matrix couldn't even be inverted? Nobody did that? I think nobody's fessing up because I saw a few that did that. Yeah, your unit test won't work if your model is under-constrained, and it turns out in OLS that makes it so your matrix can't be inverted. If that burned you, I'm sorry. I kind of assigned it to you without teaching you enough to do it well. That happens sometimes. What was that?
You throw an exception if the number of rows is too small.
Yeah, okay. So you might have seen the exception and then said, oh, well, I'll add more rows because it says to. What you didn't know is you were adding enough points that your model was at least sufficiently constrained. And then with OLS, it'll give perfect accuracy on the training data. Who knows what it'll do on the test data, right? Okay. So these are just pretty fundamental principles of machine learning, and we'll come back and talk about this principle probably more because this is kind of the core of how do you tell between a good model and a bad model. And our goal is always to get a good model, and thus our goal is pretty much usually cross-validate a lot. If ever you have a machine learning algorithm and you wonder, would this algorithm be better if I changed this equation, tuned this parameter, modified my algorithm? What's the answer? The answer is take your data, do cross-validation. If your score is better, the answer is yes, you improved it. If your score got worse, then you say, nope, whatever I did, that's worse with this data. Doesn't mean it'll be worse with some other data, but at least with this data, that gives you the answer. Is there a question?
If you start making minute adjustments in such a way that your overall cross-validation goes down, though, you're at a risk for overfitting.
That is also true, and that's another thing we need to talk about.
How difficult is that to actually do?
So that actually brings about a story. So this is actually my advisor's story, but I'll just kind of repeat the vague version I gleaned from him. So this is not very accurate, and he'll probably yell at me if this gets online and he sees it. But so he worked at a company, and they were training a neural network to do a speech recognition problem. And they were very much aware of this situation, so they took some training data and they set it aside, and they took some test data, and they were very fastidious, very careful to make sure that the test data is never cross-contaminated. No points on this side are in the test data, and they never let the model see they always destroyed their model after they tested it. Okay? So they took their neural network and they trained on the data, and then they went in with their hammer and nails and tuned it and adjusted its topology, made a bunch of changes, tweaked the algorithm. Then they wanted to see, did we do better? So they went back to their test data, measured the accuracy, Error improved a little bit, so they said, great, we made positive changes. Then they go back to their training data. They tune their model a little bit more. After some time, they go back to their test data and they say, okay, did we improve? They measure accuracy. Oh no, it didn't improve. So they undid their changes and repeat. After years of wash and rinse of this process, what happened? Yeah.
Well, the process where they're taking the results, the data, and then they're going back, that's mathematically the same as using your data in your training.
That's,
training the model with their data.
that is exactly the answer. So you've got the lesson out of it. They didn't realize this, but by virtue of the fact that they were listening to their test data in order to drive how they tuned their model, somehow information was bleeding across through the human beings into the code, and in the end they got really great accuracy. And then they took some new data that they had never seen before in the wild and tested it, and it turns out they didn't do very well on it. What was happening? They were overfitting. They had overfit the test data that they kept testing on to drive what was acceptable changes on their training data. And so it's kind of subtle and hard to intuit. You really have to make, truthfully, the test is only valid if you started over from scratch on this data and then tested for the first time ever on this test data, and then you actually have an accurate measurement of your accuracy. Now it's really hard to be that clean room, and so scientific papers come down to, we trust they know what they're doing, we take their word for it, they say they did cross-validation, we believe them, etc. But there are clever ways algorithms can cheat. Now, if you're doing optimization in hyperdimensional, 1,000-weight space, is there any way your neural network can cheat? Well, that's kind of what an optimizer does, is if there's something it can do that makes it better, it's going to change your parameters in that way, right? And so it's very common for students to not anticipate how effective these optimization methods are at finding ways to cheat. If you allow them to cheat, if you just stick some of your test data in your training data and train on it, you get good accuracy, you think everything's great, but it really might have optimized in such a way that it basically memorized those points so it can regurgitate them when you test it again. And so a little bit of care is necessary in order to get reliable numbers. Otherwise, you're actually just measuring overfit, and overfit is a nasty little problem in machine learning. Did you read about overfit in that first paper? Did he mention that? Okay, good. Now you know a little bit more what he was talking about. If you can remember what he said, then you can put it all together and learn something there. Okay, how much time do I have? Just enough time for one last point. I'm going to switch to PowerPoint mode for a moment here. Here's a picture of an artificial neural network. The inputs are called the features, the outputs are called the labels. The first layers are sometimes referred to as the input layer, the last one's called the output layer, and the ones in between are called hidden layers. Why are they hidden? Because they don't connect to the features or the labels. Therefore, they're hidden. Okay. Let's zoom in a little bit. In the past, neural networks were layers were measured in terms of, it used to be assumed that you always wanted a linear layer followed by a nonlinear layer. You can see why, right? We've proven that's an effective way. It used to be considered that a layer consisted of a linear and a nonlinear layer. That was called one layer. In more recent times, researchers have started to realize, hey, if you just call them separate layers, it actually makes the math a little easier and works out better. So I've decided to start teaching it that way. I'm calling the linear layers, which I've represented with an arrow here, one layer, and the nonlinear layers, like the tanh functions, which I've represented with a box here, a separate layer. So depending on who you ask, you could count it as one or two layers. When you read my book, you'll find it was written the old way. I just recently decided to start teaching them as separate layers. So don't get confused. This could be considered a 2-layer neural net or a 5-layer neural net, depending on how you count it. There we go. Often the output of a linear layer is called the net. This is kind of a value that's halfway through a layer of the old way of looking at it. And we call the output of any layer its activation. So the way I'm going to teach you now, the output of a linear layer is the activation of that linear layer, and the output of a nonlinear layer is the activation of that nonlinear layer. But if in the book you see the word net, that means the activation of the linear layer. With me? Okay. If we start with our features, and we pass them through a linear layer, we're calling the activate function, we compute the activation of the linear layer. Then if we perform an element-wise hyperbolic tangent on those elements, we compute the activation of the nonlinear layer. Then we multiply by the weights and add the bias, of course. Excuse me. We compute the activation of the next linear layer, also known as the net. Then if we perform element-wise hyperbolic tangent on that, we compute the activation of our nonlinear, or our tanh layer. Multiply by the weights, run it through the nonlinear layer. If we happen to have a linear layer on the end, which you can if you want, you can multiply by those weights and add the bias until finally you make a prediction of the labels. This is how we activate our artificial neural network, right? Now what we want to do here is perform gradient descent. So this represents the error surface, and we've differentiated the error with respect to all of these weights. Here's what differentiating looks like. We start by, I guess you could say, pointing the black finger of blame at the output layer. We say, how bad are those labels? And the blame term is really just the difference between the labels we wanted and the labels we actually got. Now if we multiply those by the weights, there's no bias involved, just the weights. We have the black finger of blame on the output of the nonlinear layer that preceded it. Then if we multiply by the derivative of that activation function, we compute the blame on the net, or the blame on the activation of the linear layer that preceded that. Does that make sense? Then we multiply by the weights, we get the blame on that. Multiply by the derivative of the activation function, we get the blame on the activation of the previous linear layer. We can do it again, we can do it again, and that's called backpropagation. So in a forward pass we activate, in a backward pass we point the back finger of blame and tell how bad everything is, and then we can update our weights, and that's how we update our model.